Okay, so today we are going to give a review of what we learned so far. So basically, in the last, I think, 6 weeks, we mainly focused on the two things. One is we introduced the relational data model, and then the second subject is about the design a database at high level using ER model. So for the relational data model, you need to understand several things. So what is relational data model? So relational data model basically organized data, the database data, into relations. And also we can view relations as a table. So it's pretty much, if you look at the relational database, it can be viewed as a collection of tables. Okay. And according to the relational data model, each relation has a primary key. Okay, I'm sorry, I think somehow it's not shared. Let me share it again. Okay, good. So each relation must have a primary key. So the purpose of having a primary key is to ensure that every record in the table must be unique. So we are able to distinguish each record in the table. Okay, then when we are talking about a key, so basically uh, a relation may have more than one key. Okay, so before we designate one key as the primary key, all the keys are called candidate keys. So the candidate means candidate for the primary key. Okay, then we have to pick one key, one candidate key as the primary key. Then the remaining candidate keys will be the secondary key. Okay, and also we discussed the concept, the key versus super key. So key here is equivalent to the candidate keys. So you have to understand the differences between the two. So we're going to discuss them later. Then, according to the relational data model, each attribute must be atomic. By atomic, we mean that an attribute can take only a single value and also non-divisible value. So by non-divisible means that we cannot further divide attribute value into several components. So that's called atomic. So that's kind of a requirement for the relational data model. So if you claim that you implement a relational database, you're supposed to kind of follow those requirements. So it means that every attribute must be atomic. But I think this requirement sometimes will be relaxed so that if you probably working with database, maybe some field like the person's name field, address field may actually contain multiple components. But usually it always a good thing for you to really strictly enforce the relational data model constraint. Then besides each attribute is atomic, then the other four constraints, the key constraint, entity integrity constraint, foreign key constraint, and the domain constraint. So those are the constraints that data has to meet all the time. So regardless how you change data, I mean, these constraints must be satisfied to guarantee that the data stored in the database is of high quality so people can rely on the data for the data analysis and making business decision. And then we also discussed the normal forms. So normal forms basically provides a theoretical way for us to evaluate if the organization of the data into tables are good or not. So pretty much we certify each table to see that if the table satisfies some good property, like 3NF. Okay, so we kind of discuss functional dependency first normal form, second normal form, and the third normal form. We also discussed that if a relation schema is not in third normal form, then we have to normalize it so that the original relation schema will be replaced by a set of smaller relation schemas, and each smaller relation schema is in third normal form. Okay, and also we discussed the closure of attributes. So closure of attributes provide a way for us to evaluate whether a set of attributes can potentially serve as a key of the relation. So then the key versus super key. So key satisfy both uniqueness and the minimality constraints. By uniqueness, we mean that every tuple in the table must have unique key value. Okay. And then for the minimality means that if a key contains multiple attributes, okay, so if a key contains multiple attributes, we usually call it composite key, then all attributes are needed to ensure uniqueness. Or constraint, okay, maybe constraint. So basically means no redundant attribute is allowed. Okay, so that's kind of the uniqueness means. And by minimality, I'm sorry. If a key contains multiple attributes, then all attributes are needed to ensure the uniqueness constraint. So no, basically means no redundant attribute is allowed. Okay, this is a key. Super key basically is a superset of key. Okay, so super key. So this you have to really understand the that means super key must contain a key. Okay, a super key must contain a key. Okay, so that's basically the super key means. So then you ask, why bother to have a super key if we have a key already? So I think in database, basically, if you retrieve a set of attributes that contain a key, then you know that you retrieve the tuples with a set of attributes. Okay, then you know that the resulting table, the result, basically is a collection or table of the tuples. Then each tuple must be unique because the attributes we query contains a key. Okay, so that's kind of a super key means. So I think that will pretty much help you to predict how many records or what other records will look like in the resulting table of a query. Okay, so if you select clause contains multiple attributes, and if a key if a key belongs to those set of attributes, then you know that the resulting you're going to have a unique tuple for every tuple will be unique in the result. Okay, so then the question is a key a super key? Of course, because super key only satisfies the uniqueness constraint, so it does not need to satisfy the minimality constraint. So that's why key must be a super key. Then is the super key a key? Actually depends. So if a super key only contains a key, then it is a key. If a super key contains a key plus some other attributes, then a super key is not a key. Why? Because it contains redundant attributes. Okay, so let's see the example here. So for example, we have a bank branch table. So branch ID is a key. Then we have MGR SSN, city, state, and zip. So assume that both branch ID and MGR SSN are unique for each branch. So that really indicates the bank branch has two keys. One is branch ID, the other one is MGR SSN. Since branch ID is underlined, that means that branch ID is picked as the primary key. Okay, then the MGR SSN will be called secondary key. So pick selection, the primary key is really very arbitrary. Okay, so for example, in one database, then some maybe database designer pick the branch ID as a primary key. Then if we change, if another person, he may pick the MGR as a primary key. So that's fine. So you just pick one as the primary key. Then the remaining keys are all called secondary keys. Okay. So then what is a key? So it's ask you, given these three, so which is a key? So branch ID, of course, is a key. Then the branch ID plus, so this should be yes. So this branch ID is a key. Then how about the branch ID MGR SSN together? Maybe it's better for us to use parentheses to enclose them together. It means that it's a composite. So this is no. Why it is no? Because it not only contains branch ID but also contains MGR SSN. So it means they're redundant. So we can either remove MGR SSN, then the branch ID is still a key, or we can remove branch ID, then the MGR SSN is still a key. Okay, so in this case, this is no because it's redundant. The reason is no because it's redundant, does not, it violates minimality constraint. Okay, so this is no, very important because we do not allow any redundant attributes. Then MGR SSN, according to the data description, yes, it is also key. So this is a key. Okay, so given these three options, then only, maybe I did okay, only the branch ID or MGR SSN is a key. Okay, then which is a super key? So recall that super key contains a key. Okay, so and also as long as a set of attributes contains a key, then that's super key. So then the branch ID in this case, this first option, it is yes, it is key. So it is also super key. Why? Super key only needs to satisfy the uniqueness constraint, and apparently a key satisfies both uniqueness and minimality constraint. So that's why branch ID is a super key. Second option will be MGR SSN and branch ID together. Okay, so this time it is also a super key. Why? A super key basically means that the set of attributes contains a key. So apparently both branch ID and MGR SSN is a key. So that's why both are key. So that's why the combined branch ID and MGR SSN is also satisfy the uniqueness constraint. So that is super key. Okay, not the key. So this is super key but not the key. Then the MGR SSN is yes, because why? MGR SSN is a key. So it is also super key. So every key is also super key, but not every super key is a key. So if the super key kind of converts to only key, then that super key is also a key. Okay, sorry. The next one, so this one, the branch ID and the city. So this set of attributes does contain the branch ID, which is a key. So that means that branch ID stated together is also a superkey. It's not a key because it violates minimality constraint, but it does satisfy the uniqueness constraint because branch ID is included in this set. Okay, and the second to last one, I think in this case it is also a superkey. Okay, why? Because this set of attributes does contain branch ID, the key. So that's why it's a superkey. But this set of attributes does not satisfy the minimality constraint. It only satisfies the uniqueness constraint because it contains branch ID. So the last one, the same thing. So given these four attributes or five attributes, okay, it also superkey. Okay, so that's kind of the how can we tear the superkey and the key. Key satisfy both uniqueness and minimality, but superkey only needs to satisfy the uniqueness. That really means that a superkey can have some actual attributes beside a key. Okay? Okay, so then the prime attribute and non-prime attribute. So in order to tell if an attribute is prime or non-prime, we first need to identify all the keys for a given relation schema. Then any attribute that appears in one key, then that attribute is considered as a prime attribute. And if an attribute does not appear in any key, then that attribute is called non-prime. Okay. So here give you one example. So assume we have this clinic visit. We have visit ID, then as one key. The second key is patient ID plus doctor ID plus date and time. Okay, together is a key. So then ask us to list prime attributes. So since the two keys are given, then we just simply list the attributes appears in those keys. So we have visit ID is one, then patient type. So all the attributes in the second key is also the prime attribute, okay? So it's very easy. So as long as you know what are the keys, then you know what are the prime attributes. So if you don't know what are the keys, then you will not know what are the prime attributes, okay? So then the non-prime attributes will be the remaining. So that will be the whatever left in the clinic visit schema. So it should be the P as in patient name, insurance number, and doctor last name, I think, Dr. L name, and diagnosis. I think that's it. Okay, so that's the remaining attributes that do not appear in the key. Simply means that given this relation schema, we cross out all prime attributes, then the remaining attributes will be the non-prime attributes. Question so far? Okay. Then the next one is talking about the functional dependency. So how can we examine functional dependency? Functional dependency usually define the relationship of the attributes within the same relation schema. So in this example, assume that we have a very abstract table. So the first line are the attributes name. So we have A, B, C, D, E as attributes name. Then the remaining are the records, showing the records, okay? So in database, functional dependency is represented as X, kind of this symbol means determines Y, okay? So X is called determinant and the Y is called dependent, okay? So what does this functional dependency means that given record, or a tuple. If we know the x value, then we are able to infer the y's value. Or in other words, if the records they agree on x value, then they will all agree on the y's value. Okay, so it means y's value is dependent on the x value. Okay, so now let's look at, given the data we have here, we're just trying to see if the following functional dependencies would hold. So simply just based on the limited data, we can guess, but maybe not always true, if that functional dependency would hold or not. The first one, C determines A. So in order to see if this hold, then we just simply looking for the tuples with the same C's value, and then we see if they all agree on the A's value. If yes, then that is this functional dependency is true. If no, then it is not. Okay, so I think that's a trick. We're looking for all the tuples with the same C's value. We need to make sure that they all agree on the A's value. So let's look at the table. So we have 5 tuples, and we can partition the tuple into 2 groups. The first group, they all have C as 3, so contains first, second, and the last record. Then we simply need to see if they have the same A's value. Okay, so for this first group, 3, 3, 3, we have 1, 1, 3. No, because they are not agree on the A's value. Some has A as 1, some has A as 3. So they are not agree on A's value. So this is why this is no. Okay. So that's kind of a trick. Okay, so if you look at the second group, the C has 4, and they also not agree on the A's value. Okay, so according to the functional dependency, given an X value, there is only one Y's value associated with it. Okay, so that's the requirement. Okay, so second one, D determines B. So this time we can, based on the D's value, we can partition into 2 groups. The first 4, they have the same D's value. Then the last one has different D's value. So we just need to examine for the first 4, they have the same B's value? Apparently no. So we have D as 4, 4, 4, but B as 2, 4, 2, 3. So basically means that we even have 3 B's value given D as 4. So that's violate the condition that given an X value, there's only one, that's very important, only one Y's value corresponding to it. So this also valid, this is not true. Okay. Second one, B determines D. So now we have B as 2, 2, 4, 3, 7. So we probably only need to focus on the records with the same B's value to see if they have the same D's value. So this time I think we have B as 2, and D as 4 and 4. So given these 2 records, they have same B's value, they also have same D's value. So that's why this one will be yes, at least according to the data we have here. Okay, we don't have any contradictory example to make us say no. Okay, then you may think about, how about when B equals to 2, then D equals to 4. Even B equals to 4, then D equals to 4, means that we have 2 B's value. They all have the same D's value. Is that okay? The answer is yes, because we only focus on that. Okay, given a B's value, we have one and only one D's value corresponding to it. Okay, so when B has 4, D has 4, that's fine. Even B equals to 2 and B equals to 4, they all have the same D's value. So I think that's okay. Why? Because if you assume B as zip code, I think in the class, maybe like say, for example, as D number, department number. no, again, maybe select zip, okay, not zip, sorry, B. If the B is the zip code and the D is state, the state where the zip code belongs to. So then you can tell that given state, they have so many different zip codes, but they all map into the same state. Okay, so that's okay. Okay, so several different b's value, they all map into the same this value. That's fine. But whenever we examine B determines D, we only need to make sure that for all the records with the same base value, they have only one this value corresponding to it. So they all agree on the this value. So that's the key things we need to make sure. Then the D determines E. Okay, so here, if we look at this value, the first four have the same this value, but they have different E's value. So that's really violates the definition. So this time it's no. Okay. Then E determines D. Okay. So when we look at in the E, so there's only two records with the same E's value. So ES5, they all has the same D's value, DS4. So that means this one is okay. Okay, so that's yes. Then for the C determines D. So say here we can partition C into two groups. Say with group 1 with CS3, so first, second, and the last. The group 2 with CS4, okay? So if you look at, say, group 2 CS4, I mean, these two tuple have the same D's value. So then this okay, does not violate the functional dependency C determines D. But if you look at the group 1, so first two records has CS3, DS4, but the last record CS3, but DS1. So that basically means that given CS3, we don't have we have more than one this value corresponding to it. So that's not wireless, only one. That's why it's no. Okay. Okay, so the last one, D determines C. So apparently it's not. So for the D, we just look at the first four, the DS4, then the C has two different values. So that means it is no. Okay. Any questions? Okay. Then for the transitive functional dependency and the partial and the full functional dependency. So this transitive partial full basically in terms of the key definition. Okay. So given relation R and the functional dependency X determines Y defined on R. If X is a part of key but not the whole key, then X determines Y is partial. So by partial means that Y is only dependent on a partial key, not the whole key. Okay? Then given a relation R, so X determines Y is transitive if both X and Y are non-prime attributes. So now we can know that, okay, so this is transitive. But transitive means that Y is actually directly dependent on X, which is a non-prime attribute. And it is not directly dependent on the primary key. Okay, so this is transitive. The transitive basically means that based on why we call it transitive, because there's default FD, basically the primary key, for example, determines all non-prime attributes. Okay, So then, since X is a non-prime attribute, so that means that the primary key determines X, and then X determines Y, because that's the functional dependency given. So Y is transitively dependent on the primary key. Okay, so that's the reason. Okay. So default functional dependency basically means that primary key determines all non-prime attributes. Then given X and Y both are non-prime attributes, so then we can tell that primary key determines X. Then we given the functional dependency X determines Y, then we can tell that Y is transitively dependent on the primary key. So that's kind of the things. How do you identify the transitive functional dependency? So given X determines Y, if both X and Y are non-prime attributes, then this is called transitive. Okay. So then X determines Y is a full functional dependency if X is a key. So we kind of this key can be the primary key or can be the secondary key. So as long as X is a key, then X determines Y is okay. It's called a full. Okay. So in the normal forms, partial and transitive functional dependencies, they are not good. They are bad. So we try to avoid them. Okay. So here give you one example. So we have relation student name, last name, student ID. I don't think that's the course number, course name, and the grade. I think that's not the right. Should be the student ID and the course number. Sorry, the primary key is marked wrong. So okay. So given this relation, we have a composite key. Okay, then we have several non-prime attributes. So with following functional dependency, identify partial, transitive, and full, if any. So student determines L name. Since student is part of this key, because key contains both student and the course number. So student is not the whole key, but student is a component of the key. So that's why student is called a partial key. So this means partial functional dependency, okay? Because student ID is part of the key, but not the entire key, okay? Then the second one, course number determines course name. So this is also partial. Because course number is what? Course number is the also partial key, not the whole key. Okay. Then the last one, student ID and the course number determines grade. So now the determinant is a whole primary key. Okay. So then whole primary key as determinant, then this functional dependency is called a full functional dependency. Okay. I may revise it so you may have a more for example, I also have assumed that department, for example. Okay. So I'm adding one attribute, department, and also I'm adding one functional dependency. So I just simply revise this question. So now we have course number. Maybe it's not the. Let me see. Yeah, if I use course name. Okay, so add two attributes, maybe called DPT name, then DPT telephone number. Okay, so then I can add maybe one more. Okay, so this is a two more functional dependency if assume that I added two more attributes, DPT name and the DPT telephone number in the schema. Then we have two more functional dependency. So FD4 course number determines course name, department name. Okay. So then the FD4, since course number is still part of the key but not whole key, then the FD4 will be the partial. Okay. Then for the FD5, this time DPT name is not partial key, so it's actually a non-prime attribute. How do I know it is non-prime attribute? Because it does not belong to the primary key. Okay. Then DPT telephone number is also a non-prime attribute. So given this FD4, we have both determinant and dependent as non-prime attribute. So that really indicates this is transitive FD. Okay. Anyway, so this is how I'm just letting you know that how to identify the partial, full, and the transitive. And then usually probably you want to, before you're able to answer the question, you probably first list the prime attributes so that you can know what are the non-prime attributes. And it can help you to identify the transitive functional dependency. Okay. So let me save this one to a different file. So okay. So then for the prime attributes, as will be student ID. So whatever attributes appear in a key, those attributes are the prime attributes. For the non-prime attributes, that will be the attributes does not appear in any key. So in this example, we assume the relation has only one key. Okay. So then DPT name, DPT telephone, and the grade. So those are the non-prime attributes. Okay. So based on the prime, non-prime attributes, we can easily tell that the FD5, both determinant and dependent, are the what? Are the non-prime attributes. So that's why this is called transitive functional dependency. Okay. So this shows that why partial FD and the transitive FD are bad. So because if given the partial functional dependency, X determines Y is a partial, that means that X is a part of the key but not the whole key. Since it is a part of key but not the key, that means that in the database table, it is possible that multiple records they have the same X value because they are allowed to have same X value because X is not a key. Then based on this functional dependency, they all agree on the Y's value. So that's kind of a one root cause for redundant information showing in the database. Okay. Similarly, for the transitive functional dependency, X determines Y, and X is a non-prime attribute, so has nothing to do with the key. So a non-prime attribute will not unique has unique value for the records in the table. So if the X does not have a unique value because it's non-prime attribute, then we can tell that it is possible that multiple records have the same X value. Then based on this functional dependency, they all have the same Y's value. So that's kind of repeating of X and Y in a database, the same values is also considered as redundant. So in general, um, partial functional dependency and transitive functional dependency are both the root cause of the data redundancy issue. Okay. So the conclusion, partial FDs and transitive FDs are the root cause of data redundancy. Okay, so that's why they are not good. So they are bad, they're not good. Okay, so partial transitive definitely not good sign. So if you see some partial or some transitive functional dependency that defined on the relation schema, you know that that relation schema needs to be normalized. Then I think in the relational data model, we also studied the closure of attributes. Basically given a set of attributes, and given the functional dependency defined, then we can kind of calculate the closure of a set of attributes. Okay. So we thus study what is the closure of the attributes. So given the A1, AN is a set of attributes and S is a set of functional dependency. So the closure of A1, A2 all the way to the AN under this functional dependency is a set of all attributes that are functionally dependent on the original set A1, A2 all the way to the AN. And with respect to S, so with respect to the functional dependency. Okay, so we usually use this notation like the supercate and super plus sign to indicate the closure. So we enclose the set of attributes using curly braces and then has a super plus sign to indicate the closure. Okay, and also there is kind of trivial rules, means that the set of attributes, the closure of set attributes will contain itself. Okay, so that's basically given A1, A2, AN, then its closure will contain A1, A2, AN. That's considered the trivial functional dependency. And this shows the algorithm for deriving the closure of set of attributes. So basically we initialized the closure with original A1, A2, and AN. Then we examine the functional dependencies for a functional dependency which contains, okay, the first step, which contains the attributes belong to the set A1, A2, AN. Then we're going to use that functional dependency and then add the dependent to the closure set. Okay, so we're going to repeating the steps. So pretty much we're going to examine every single functional dependency to determine whether the functional dependency's determinant is covered or included in the closure. If yes, we're going to add the corresponding dependent to the closure. So in this case, we kind of grow closure kind of step by step by qualified functional dependency until we no longer be able to grow it. Then the resulting set of attributes will be the closure of the starting attributes. So let's see the example here. Okay, So how when we have kind of relation schema, in this case we have a relation schema, and then we have a set of functional dependency defined on that. So now if we try to calculate the closure of A and B, then it will start with A and B. So that's considered as a triple, okay? Then we're going to growing it until we won't be able to find any. So we start with A and B. So that's we initialized the closure as A and B. So that's the attributes. We start with, okay, A, B. Then we're going to examine the functional dependency here to see is any functional dependency whose dependent either is A or B or A and B. So in this case, only the first one. The second one, it has B but also C. We don't have C here. The third one, it has D. We don't have D here. And the last one, CF, we don't have any C and F. So that's why we're going to use A, B, this functional dependency. So we're going to group because A, B determines C. So that means that we're going to put C into the closure. Okay, so by this functional dependency, we grew AB to the ABC. Okay, now we have ABC. Now we're going to see is there any functional dependency whose determinant is included in ABC. So I think since we use ABC, we will no longer consider it. So now we have BC determines AD. Okay, so BC is included in this closure. So that's why we're going to apply BC determines AD. So we're going to suppose we're going to add both A and D into the closure. But since A is already included, so that means we only add D because A is already in there. So now we have using two functional dependency. The next step we're going to examine how about the remaining two. So D determines C, yeah, it's okay because we do have D in the closure set. So it means that we are able to apply this functional dependency and add the E to the closure. Okay. Now we still have last one. So now if we examine the last one, it's called the CF determines B. Apparently we have C, but we don't have F. So that means this one will not be able to use to grow. So finally, we're going to have this last status of the closure set at closure of the AB. Okay, so there's the last one we grow, and that's the end. So the closure of AB will be A, B, C, D, E. Okay, let's look at the second one. So B, C. So we initialized closure with this attribute self. Okay, then we're going to examine. Given the BC, are we able to grow? So now we have BC determines AD. So it means that we can use BC determines AD because we have both B and C in the initial closure. So that's why we're going to have BC AD. Okay. By BC determines AD. Okay. Now we have ABCD. So then next one. Okay. Let's see. We can actually two satisfy. One is D determines E, the other one is AB determines C. So we can apply them one by one, okay? So you can, in any order. So I just want to step-by-step approach. So probably start with AB first. So because, B, C, A, D, okay. That's a good question. So we have AB determines C. So AB is included in here. So then according to this functional dependency, we only need to add C to the closure. But we already have a C. So that means AB determines C. Even we apply this functional dependency, we won't be able to group the closure. So that's why we're going to use D determines C. Okay, it's because E is not in the original set. So we're going to have E here. Okay. So I just want to don't cause you confusion. So this indicates that AB determines C. Applying AB determines C will not change the closure. Okay. So that's kind of the reason. Even we apply by AB determines B, AB determines C, then the closure will not change because both A, B, and C have already been in the closure. Okay. So the next one, the CEB determines. I think we won't have enough time to determine. Okay, CE determines, CF determines the CF closure. So we initialize as CF. Then we're going to add. So when we examine what we can apply. So in this case, only last functional dependency can be applied to. So that's why we have C, F, B, by CF determines B. Okay, so it means CF appears in the original set closure. Then based on CF determines B, we add B into the closure. Now we have CFB. Then which we are going to grow. So we don't have AB here, but we do have BC. Okay, so then next time we're going to apply. We're going to apply BC. We are both B and C included in the closure. Then we can apply BC determines AD. So then we add AD to the sets. Okay. So now I think it is. Do we have anything? Yeah, we actually have more. So once we apply BC determines AD, we have D determines E. Okay. We also have AB determines C, but AB determines C will not help us grow because both AB and C are already included in the closure. So that's why the optimized process we're going to apply the D determines C. Okay. So now actually if we look at this one, with the closure, we're no longer able to grow because closure right now contains all attributes A, B, C, D of the relation. So I think AB will not be useful. BC determines AD we have applied already, and D determines C, and the CF determines B. So also will not help us grow because CF already in the relation. Okay, so the final CF and B in the relation in the closure. So that's why we will not be able to grow any more attributes using CF determines B or AB determines C. So now we stop. Okay, but if we compare the closure of CF with the attributes in the relation schema, then you can tell that closure of CF contains all attributes in the relation. So that indicates at least CF is the super key. Then we just need to examine if CF are needed. So when the easiest way that we just simply calculate C and F's closure to see if what the C's closure, what the F's closure, because that's a subset of the CF. So C's closure, if we look at the function dependency, the C's closure will be C. Why? Because there's no functional dependency who has determinant as C. Similarly, for the F, I think the same. So we don't have any functional dependency whose determinant is C, is F only. Although we have CF, but this will not be applied because we only have F and we don't have C. So that means that given CF, the closure cover all the attributes of the relation, but C's closure does not cover all the attributes of the relation, and F's closure does not cover all the attributes of the relation. Then we can, so therefore CF is minimal or satisfy the minimality. Minimal identity constraint. So it is a key also. Okay. So this shows the how do we calculate the closure. And then, yeah, I think we may have round of time. So then the normal form. So I strongly encourage you to working on the normal form and the ER design. Okay. Then we're going to show the solution to the next class on the Tuesday, and the Thursday then we will have the term exam. Okay, so I think for preparing the normal form normalization, you can go over the slides of the normalization part, and we do have several in-class exercise. And then for the ER design, I think we also have two in-class exercise and also one assignment. So you can go over the in-class exercise to understand how to design the ER diagram. So the next Tuesday, we're going to review the normalization and the ER diagram. And then hopefully you're ready on Thursday for the term exam. Okay? Okay, any questions? So if you have questions, you can text me. I'm not sure if my speaker is working. So if you don't have questions, then we are done for today. Thank you.